Hello guys, it's Miss Wilson. So sorry I can't be there with you today, but we will still have our lesson as planned. I want you, as we go through the lesson, to do this as we would a regular class. So if you do have questions, someone will be there to pause the video and answer them for you to clarify. Also, if I ask a question, I'm going to give you some time and I would like you to also answer those questions. And someone will be there to make sure that your answers are correct. Also, as you're taking notes of this video, sometimes it might go a little fast in the sense that I might have some things already pre-written. Do not feel like it's going too fast. You'll have plenty of time to re-look at the videos. I will give you access to the video so that you can go back through it and take notes at your own pace. So don't feel discouraged if you can't get everything written down. You'll be able to get it at your leisure. And then lastly, we'll do problem sets in between to make sure that everyone is understanding the material as we go through it. So sit back, relax, and let's start our matrices. So the next section that we're going to cover is 8.1, and this is matrices and systems of equations. So we've seen 4 different techniques for solving systems of equations. And the last technique we saw was Gaussian elimination. And so now we're going to use this same technique, but use something new, which we're going to call a matrix. A matrix, and when we use the matrix is the singular form of a matrix, or we say matrices for plural. It is a technique we use for solving a system of linear equations. So we say if we have a m by n matrix, we say the if m and n are positive real numbers, we say an m by n matrix is a rectangular array with rows and columns. A matrix is written in brackets, not braces, not parentheses, but brackets. And so we have different columns, and each what we call entry is written as this is our first row and our first column. So this is row 1 and column 1. And then row 2 would be, our next entry will be A1, 2. And so the M, which is the 1 here, represents our row. The N, this is our second, represents our column. So also the third would be a A1, 3, ... up to A1N, and this is our nth column. Okay, and our second row would be, in first entry would be A2, 1, A2, 2, A2, 3, up to A2N. And then we have A3, 1, ... down to AM1. Let's erase that. So this is our mth row, and then AM2, AM3, ... up to AMN. Again, each entry we're going to say is some A sub ij, where we have the ith row and the jth column. So we call m by n the order of our matrix. So if there are 2 rows and 3 columns, we say we have a 2 by 3 order of our matrix. If m is equal to n, say a 3 by 3, we call this a square matrix. Then if we look at the entries A11, A22, A33, etc., and we noticed here, this is what we call our main diagonal of the matrix. We'll use this information in some later sections. So let's look at these matrices. And we want to look at them, and I would like for you to tell me the order of the matrix. Again, the order of a matrix is M by M, N, where M is the row and N is the column. So A. Can someone please tell me what the order of this matrix is? So it has one row and one column. So this is what we call a 1 by 1 matrix. What about B? B, the order would be 1 by 4, 1 row, 4 columns. What about C? This would be a 3 by 1 matrix. D, so this would be a 2 by 2 matrix. We also notice that since M is equal to N, we call this a square matrix. What about E? Very good. E would be a 2 by 3 matrix. So we notice we actually have a special kind of matrix here. So when we only have one row, we call this a row matrix. And notice in C, when we only have one column, we have what we call a column matrix. Now let's look at this system of equations. This is a system with 3 equations, 1, 2, and 3, and 3 unknowns, x, y, and z. So the first equation, x minus 4y plus 3z is equal to 5, minus x plus 3y minus z is equal to negative 3, and 2x minus 4z is equal to 6. So how is this system of equations related to our matrices? Okay, so we can actually write this matrix and write a matrix of this system using what we call an augmented matrix. Okay, so we make a matrix. In an augmented matrix, we put the coefficients as well as the solution into this array. So the coefficient of this term here is 1. The coefficient of the next term is negative 4. And then we have 3. And what we're going to do to separate our coefficients from our solution, we're going to make a line. And so then our solution is 5. So please tell me what the entries would be for the next row. Negative 1, 3, negative 1, and then our solution, negative 3. Then we have 2. What about the next entry for my y term? Since there is no y term, we will put 0 as our entry because we know that that's the same thing as 0 times y. Then we have negative 4 and 6, and this is my augmented matrix. We're going to call each of these a row. This is row 1, row 2, and row 3. Okay. And so what would the order of this matrix be? The order of this matrix would be, very good, a 3 by 4. We include the column for the solutions. Now, let's talk about what a coefficient matrix would look like. So what do you think a coefficient matrix would be? A coefficient matrix is exactly what it is. It is just a matrix of the coefficients. So we have 1, negative 4, 3, negative 1, 3, negative 1, 2, 0, negative 4. And so our coefficient matrix, we notice, is a 3 by 3 matrix. Once I have a matrix, I can perform what we call elementary row operations, which I'll probably say EROs from now on. So EROs are elementary row operations. If we perform one of these elementary row operations, it will not change our matrix. It gives us an equivalent matrix. So the first thing we can do is we can interchange two equations and we will still have an equivalent matrix. Number 2 says we can multiply an equation by a non-zero constant. So that means we can multiply a row by a non-zero constant. And 3 says we can add the multiple of an equation to another equation. So we can multiply a constant multiple by one row and then add it to another. So we want to perform the following EROs to the matrix below. So we want to add 2 times the first row of the original matrix to the third row. So let's look at our original matrix. Our original matrix is 1, 2, negative 4, 3, 0, 3, negative 2, negative 1, 2, 1, 5, 2. So we're going to use this notation here. Because we are adding 2 times the first row of the original matrix to the third row is the row that will change in value. So we're going to use this notation here, which says I'm going to multiply negative 2 times row 1 and add it to row 3. It is going to be beside the third row. And since the first and second row do not change, I just rewrite them. So I have negative 1, 2, negative 4, 3. My second row will become 0, 3, negative 2, negative 1. Now, I need to perform my ERO. Our ERO says we want to take 2 times the first row. So 2 times 1 is 2 and add it to so negative 2. So negative 2 times 1 is negative 2 and add it to the third row. So negative 2 plus 2 gives us what? 0. Very good. Now let's look at negative 2 times 2, which is a negative 4, and add that to 1, and we have what? A negative, it's a negative 3, right? So negative 2 times negative 4 gives me a positive 8. A positive 8 plus 5 gives me 13. Then we have negative 2 times 3, which would be what? 6. And 6 plus a negative 2, we're doing it wrong. Negative 2 times 3 is a negative 6. And negative 6 plus negative 2 is negative 8. And so we say that this is a new row equivalent matrix by using our EROs. So now we're actually going to take a pause and do the problem set 1 on your worksheet. Now let's look at this system of 3 equations and 3 unknowns. This is actually a system that we have looked at in our last section, but now we're going to solve this system using our matrices and elementary row operations. So our system is x minus 2y plus 3z is equal to 9, negative x plus 3y is equal to negative 4, and 2x minus 5y plus 5z is equal to 17. So the first thing when we get a system is we want to write, the associated augmented matrix. So let's write this matrix. So we first will have what? 1, negative 2, 3, and 9, negative 1, 3, 0, please remember to include our zeros, negative 4, 2, negative 5, 5, and 17. And so this is our associated augmented matrix. Now, just as we did with Gaussian elimination, we want to get it into row echelon form. And again, what is row echelon form? Okay. Very good. Row echelon form, we wanted to get it in a stair-step pattern. So therefore, we notice that we have 1 as our first entry. And so since 1 is our first entry, then we want to next for our second row, we want to get rid of this negative x. So how can we get rid of this negative x? We notice that what would we do if this were a system? We would just add row 1 and row 2 together. So what we're going to do is for our next matrix, we're going to add row 1 and row 2. But just as we've done before, now we're going to use our notation. The first row is not changing, so it will remain the same. But our second row, what are we going to do? We are adding row 1 to row 2. So we want to make sure again that we put that in front of the second row. And so let's do that. If we do 1 plus negative 1, we get 0. If we do negative 2 plus 3, we get 1. Then 3 plus 0, we get 3. And then 9 plus negative 4, we get 5. And so the third row is not changing, so we will leave it as it is. And so now our new matrix would read as it is, but now we've gotten rid of this second row. And so just as we don't want that there, we don't want, this here. For our next set, what don't we want? We want to get rid of this term and this term here. So we always start from left to right. And so what do we want these to be in our matrix? We would like for them to be zeros. Okay. So our next step, let's do our matrix. The first row and the second row will remain the same. 0, 1, 3, and 5. But how can we get rid of that 2? Okay. And so we want to always work from left to right. It looks like what we can do is if we multiply the first row by a negative 2 and add to row 3, we will get that 0 that we're looking for. So we have negative 2 plus 2, which will give us the 0 that we want. And then we'll have negative 2 times negative 2, which is a positive 4, plus a negative 5, and that will give us a negative 1. Negative 2 times 3 is a negative 6, plus 5 gives us a negative 1. And then we have negative 2 times 9, which would be negative 18, plus 17 will give us a negative 1. So now looking at the matrix that we just had from our last slide, it is as it is at the top. So we also notice now we have a 0 entry here and a 0 entry here, which means that I have a x, y, and z term for my first one, and just a y and z, and a y and z for my second. So the next thing I would like to get rid of is this negative 1, so that we will only have a z term in my last equation. So how can we get rid of this negative 1? You may notice that I have a 1 here, so that means if I add row 2 to row 3, then I can get a 0 in this place. So the first 2 rows don't change. But my last row, I want to add my entries. Okay? And so if I add my first, I do a 0 plus 0, and I remain a 0. Then I do my 1 plus negative 1, and I get a 0, which is what I want. Then I do 3 plus negative 1, and I get a positive 2, and then I do 5 plus negative 1, and it leaves me with a 4. Okay. What is the last thing for my row echelon form? So for my row echelon form, I would like to have 1s on this diagonal. So we must make this be here because that means that the leading coefficient is now 2. What can I do using my elementary row operations to change this value? Okay, I notice that if I divide, well, let's just say multiply by 1/2, because it says we can do a constant multiple of a row, and then we can do this entry. So I first two rows remain the same. 1, -2, 3, 0, 1, 3, 5, and then I have 0, 0. When I do 1/2 times 2, I get 1, and when I do 4 times 2, I get 2. And so what I want to do is come back here and rewrite my now resulting matrix. So if I rewrite this matrix, what do I get? I get x minus 2y plus 3z is equal to 9. Then I have y plus 3z is equal to 5. And I have z is equal to 2. And so this system is equivalent to the first system that we looked at. And so lastly, to solve this system, we're going to back substitute. So we've done this several times. When I back substitute, we should get the values 1, -1, and 2. And so you can plug those in to make sure that those are indeed correct. And so we now have a solution to our system, but we've used row operations, elementary row operations, which are EROs, to solve it. So let's now talk about when a matrix is in row echelon form. So the first thing, if a matrix is in row echelon form, is if any row that consists entirely of zeros will occur at the bottom of the row. So we notice here that the row with zeros is at the bottom of the matrix. Number 2, for each row that does not consist entirely of zeros, the first non-zero entry is a 1. And we're going to call this the leading one. So in this second row, there's a 0, but the first non-zero element is a 1. And then the third row, we notice this here. So let's just notice here, we still have this stair-step pattern. But now we have 1s on our diagonal. And 3, for 2 successive non-zero rows, the leading one in the higher row is further to the left than the leading ones of any of the lower rows. Okay. And so these are our 3 rules. So let's go through them again. Okay. Any row consisting entirely of zeros occurs at the bottom of a matrix. For each row that does not consist entirely of zeros, the first non-zero entry is a 1. We're going to call that our leading one. And for 2 successive non-zero rows, the leading one in the higher row is further to the left than the leading one in the lower rows. So let's look at some examples of what we call matrices in row echelon form. So this first matrix here is in row echelon form because our leading entries are 1 if it is a non-zero, so we're good here. Okay, and the first entry here is not a 1, which is fine, but it's a 0, so we still have this here, row echelon, and our row of 0 occurs at the bottom, so it's row echelon. Okay. And same thing here. And our row of zeros is at the bottom. Okay. But we do notice something kind of special for this second and third entry. Okay. When we have a matrix that's in what we call reduced row echelon form, if we have a leading one, so we notice we have a leading one, it has zeros above and below it, then we say it is reduced row echelon. So this leading one has zeros below, and this leading one has zeros above and below. So we say that this is reduced row echelon. Okay. Same thing here. We have all my leading ones have zeros above and below, so we're fine. There is no leading one in this fourth column, so it doesn't matter that those entries are not 0. Okay? If we look at 1, the first column has zeros below, but once we have this column that does not have a 0 above the leading one, we would not say that it is reduced row echelon. So now we're going to take a pause and do our problem set number 2. Now let's look at an example of a 4x4 matrix. We want to use Gaussian elimination with matrices and back substitution to solve this system. So what we're going to first do is I would like for you to write down the associated augmented matrix that goes with this system. Y plus z minus 2w is equal to -3. X plus 2y minus z is equal to 2. 2x plus 4y plus z minus 3w is equal to -2. X minus 4y minus 7z minus w is equal to -19. If you could pause the video and have everyone write down the associated augmented matrix. Okay, so everyone's augmented matrix should look like this. 0, 1, 1, -2, -3, 1, 2, -1, 0, 2, 2, 4, 1, -3, -2, and 1, -4, -7, -1, -19. So the first thing we notice is we want to get this into row echelon form. So we notice that for this leading one here, it is not in the correct position. So let's take that away. And we want to actually get it in its position. So how can we get it in its position? We can switch row 1 and row 2. So we notice that that means that row 1, we're going to use this notation here. That means those are double arrows going in both directions, meaning we are switching row 1 with row 2. So now row 1 becomes 1, 2, -1, 0, and 2. And then row 2 becomes 0, 1, 1, -2, -3, and the other two rows remain the same. Okay, very good. And so we notice with that switch, we have our run as a leading one here, and gratefully, we have a leading one here too. So what's the next thing that we would like to change? Okay, and so this is the order we want to go in. We want to actually get zeros here under this leading one. Okay, and so we're going to now, in our next step, we're going to change, how do we get to row 3 to become a 0, the 2 there in that entry. So the first thing we're going to do is we're going to write the first 2 rows because they're not going to change. So what can we do to row 3 so that that entry becomes a 0? I notice if I multiplied -2 times row 1 and add it to row 3, I should have a 0. Let's make sure. -2 times 1 is -2, plus 2 gives me 0. Wonderful. -2 times 2 is -4, plus 4 also gives me 0. Great. Negative 2 times negative 1 gives me positive 2 plus 1, which is a 3. Negative 2 times 0 is 0, plus negative 3 is negative 3, and negative 2 times 2 is a positive 4, plus negative, is a negative 4, excuse me, plus negative 2 is a negative 6. And so we actually can also, we're going to learn now that we don't have to, since the fourth row, we can also change it and not affect any of the earlier rows. We're going to also go ahead and change that 1 that is here into a 0 also. Okay, so we're going to do it all in one step. How can we get that to become a 1? A 0. If I do a negative of row 1 and add it to row 4, then we will get a 0 in that entry. So negative 1 plus 1 is 0. Negative of 2 plus negative 4 gives me negative 6. And then negative 1 becomes a positive 1 plus negative 6 is negative 6 again. And then 0 plus negative 1, and negative 2 plus negative 19 is a negative 21. Okay, and I'm going to try to keep it all on this page. Bear with me. Okay, so now what do we have? What do we want to do? Okay, we got, thankfully we have a 0 here. We have a 0 here. Okay, we have a 0 here, so that's great. We got our stair step pattern. So what is the next thing? We got to get this negative 6 to also become a 0. So let's do that. How can we do that? Any ideas? Okay, so we want to make sure that we choose a row that doesn't affect any other rows. What if I were to choose this? Let's choose this 2 here. What if I said 3 times row 1, which would be 3 times 2 is 6, and add it to that negative 6, and I get a 0, right? But what's going to happen to this term here? If I do 3 times 1, I'm going to get 3 plus 0, which is going to leave me with a 3 there, and we want that to remain a 0. So we do not want to do that. So when we're looking at this column here, since we're looking at this column here, we don't want to do anything above where this 1 is that we have for this row. Okay, let me see. So what can we do with that? It looks like if I do 6 times row 2 and add it to row 4, then I should be able to get a 0 there. So let's do that. Let's see, my first 2 rows will remain the same. Let's change that. 1, 2, negative 1, 0, and 2. 0, 1, negative 2. Ooh, sorry. That's 1, negative 2, negative 3. 0, 0, 3, negative 3, negative 6. And then let's now do our operation. We said we're going to do 6 times row 2 and add it to row 4. And so this first term will remain 0. 6 times 1 plus negative 6 is 0 again. 6 times 1 again, added to negative 6 is 0. 6 times negative 2, which is this term here, okay, is negative 12 plus negative 1 gives me a negative 13. And then 6 times negative 3 is a negative 18 plus the negative 21 is a negative 39. Looks good so far. Now, I look like I'm almost in row echelon form, but what do I notice? I have a 3 here and a negative 13 here. We want these values to be 1, right? So we want our leading ones there. So let's work with the 3 first. How can we get that to change? So the first 2 rows are going to be the same. 0, 1, 1, negative 2, negative 3. what can we do to this row? We want it to be a 1. So we can do 1/3 of row 3. So we can multiply by 1/3, and what do we get? 1/3 times 0 is 0, again is 0. Now we have a 1, and then this will give us a -1, and this value give us a -2. Okay, what can we do to this 13 here? Very good. We can multiply by a negative, let's make that, okay, -1/13, row 4. Okay, very good. So we get 0, 0, 0, 1, and 3. So if I look at this, let's rewrite the new augmented matrix that we have. So what would this be? You take the time and write it with me. We'll have x plus 2y minus z is equal to 2. We have y plus z minus 2w is equal to -3. Then we have z minus w is equal to -2. And then we have w is equal to 3. And so we say that this matrix is equivalent to the original matrix that we have. And so now if we do back substitution, which I won't do, we already see our w is going to be equal to 3. So our x, y, z, w will be -1, 2, 1, and 3. And then you want to check your solution to make sure that it is indeed correct. Now, let's look at this matrix. Do we notice anything funny, cool, something right, something wrong with this matrix? Does anybody see anything? Okay. Well, if we look at this matrix and we were to write it back into a system of equations, when I would write this line here, I would notice I would have a line that says 0 equals -2. Does 0 equal -2? It does not. So we saw in a couple sections ago, if I have a false statement, so if I have a statement that is false, then we say this system has no solution. So now I would like you to pause again and work on problem set number 3. Okay, now that you've worked a few problems, let's look at, okay, ignore whatever just happened. But now that what we're going to do is look at what we call Gauss-Jordan elimination. So we saw our matrix, we wanted to get them in row echelon form. And so what we want to do now is we want to get our matrices in reduced row echelon form. So we would have something of the sort. Okay. We notice that this is reduced row echelon because each leading one has zeros above and below. And then do you notice something special about reduced row echelon? Once we get it into reduced row echelon, we can actually just write our system and we will have x equals 2, y equals 4, and, z equals 3. And so we automatically, once we go just a little further and get our our system into a matrix into reduced row echelon, we actually have the solution to the system. So let's look at a system that we actually solved. The first example we solved. 1, -2, 3, and 9, 0, 1, 3, 5, and 0, 0, 1, 2. So this was the last matrix that we did, and we did back substitution. But now what we're going to do is this Gauss-Jordan elimination. And Gauss-Jordan says, let's get it into reduced row echelon. So the strategy is to first get it into row echelon form, and then we're going to work our way back up. So we're going to start with this term and then this term and this term to get these zeros. Okay? So we've gotten into this form. So how can we get this -2 to become a 0? Okay, so let's see. We can do what? 2. Let's do this. Let's just take this off and get it over. 2 times row 2 and add it to row 1. So we'll have 1, 2 times row 2, that will become 0. And then here, 2 times 3 is 6, 6 plus 3 is 9. And then 2 times 5 is 10, plus 9 is 19. And then our second row we'll just keep the same. So I should have done this in a better order, but for space, let's put the next one here. Okay, and so how can we get now this 9 to become a 0? Looks like I can do -9 row 3 plus row 1. So we'll have 1, 0, and then -9 times 1, this one that's here, plus the 9 is 0. And then we'll have what? -9 times 2 plus is -9 plus 19 is 1. I mean, -9 times 2 is 18. Sorry about that. And then let's go ahead while we're here and go ahead and make this 3 a 0. So what can we do? We'll have what? -3 row 3 plus now row 2. 0, 1, those will remain the same. And -3 plus 3 is 0. -3 times 2 is -6 plus 5 is a -1. And then my last row remains the same. And so now we get my system, which says x is equal to 1, y is equal to -1, and z is equal to 2. And if you look back in your notes, this is the same thing we have here. So now I would like you to work the last problem, set number 4, but when you work it, I would like you to use Gaussian Gauss-Jordan elimination. And we are done with section 8.1. Thank you for your time. Feel free to look back through this video and go through it extensively and take notes as you go through it. And have a wonderful evening.